Whether your child is in elementary school or preparing for college applications, software tools are now as important as pencils and textbooks. But not all software is created equal. The best educational tools share three qualities. They are easy for students to use independently, they complement rather than replace real thinking and effort, and they give teachers and parents useful insight into a student's progress. These qualities reflect a clear trend. Digital learning is not a temporary experiment. It is now a permanent part of how schools operate, and students who know how to use these tools well gain a real academic advantage. Software has changed the way teachers deliver lessons. Instead of standing at a chalkboard and hoping every student follows along at the same pace, teachers can now use digital platforms to present information in multiple formats: video, audio, interactive exercises, and written explanations, so that students with different learning styles all have a way in. Assignments no longer need to be handed in on paper and returned days later with a grade. Digital submission tools allow teachers to provide feedback the same day, sometimes within hours. That speed matters enormously. A student who understands immediately where they went wrong can correct their thinking before a misunderstanding has time to deepen into a long-term gap in knowledge. Attendance, progress tracking, and communication between teachers and parents have also improved dramatically. A parent who once had to wait for a quarterly report card to find out how their child was doing can now check a dashboard in real time and see exactly which assignments are complete, which are missing, and how their student is performing across every subject. For students with different learning needs, software has opened doors that were previously closed. Adjustable text sizes, read-aloud features, closed captions on videos, and customizable pacing mean that a student who struggles with traditional classroom instruction can now access the same material in a format that works for them. Inclusion, once a logistical challenge, has become far more achievable with the right digital tools in place. Collaboration has also transformed. Students working on group projects no longer need to be in the same room or even the same time zone. Shared documents, group messaging tools, and real-time editing platforms allow students to divide work, give each other feedback, and produce polished final results together, building the teamwork and communication skills that every employer values. Research has moved almost entirely online. Digital libraries, academic databases, and reference tools give students access to a depth and breadth of information that no physical school library could match. Learning to navigate these resources, evaluate the credibility of sources, and cite information properly are skills that serve students throughout their academic careers and into professional life. Perhaps, most importantly, software connects school to the real world. When students use the same types of tools that professionals use every day, word processors, spreadsheets, presentation software, project management platforms, they are not just completing schoolwork. They are building practical competencies that will serve them in college, in internships, and in careers across every industry. The question for schools and families today is not whether to use educational software. That decision has already been made by the direction of the world. The real question is how to choose the right tools, use them wisely, and make sure that technology always serves the student, and never the other way around. Science for students, handout Why Every Student Should Learn to Code. Not long ago, coding was considered a niche skill, something pursued by a small group of highly technical people who wanted to build software for a living. That perception has changed completely. Today, coding is understood as a fundamental literacy, as essential to a student's education as reading, writing, and mathematics. The reason for this shift is straightforward. Software now powers nearly every aspect of modern life. The apps on a smartphone, the systems that run hospitals, the platforms that process financial transactions, the tools that scientists use to analyze data, the algorithms that recommend what to watch or listen to next. All of it is built on code. A student who understands how software works is not just better prepared for a career in technology, they are better prepared to participate in the world as it actually exists. But coding is not only about career preparation. At its core, learning to code is about learning to think. Programming teaches students how to break large, complex problems into smaller, manageable steps. It teaches them to look for patterns, to think logically, to test their ideas, and to learn from their mistakes in a structured way. These are not just programming skills, they are thinking skills that apply to every subject a student will ever study and every challenge they will ever face. Computer science goes even further. It is the academic discipline that underpins all of software development, covering topics from algorithms and data structures to artificial intelligence, cybersecurity, networking, and the theory of computation. A strong foundation in computer science does not just teach students to write code. It teaches them to understand why certain approaches to problems work better than others, and how to design systems that are reliable, efficient, and secure. The right age to start. One of the most common questions parents ask is, when should my child start learning to code? The answer, supported by decades of research in child development and education, is that there is no age too young to begin, as long as the approach matches the child's developmental stage. Young children, even those who cannot yet read fluently, can begin developing the logical and sequential thinking that underpins programming. Simple activities that involve following step-by-step instructions, sorting objects by category, or identifying patterns in sequences all build the cognitive foundations that make coding easier to learn later. Purpose-built software tools for early learners translate these concepts into visual, game-like environments where children drag and drop blocks to make characters move, collect objects, and solve puzzles. The child is learning the structure of code without ever seeing a line of typed syntax. By the time students reach middle school, they are typically ready to begin working with text-based programming languages. At this stage, the concepts become more abstract, and students start to see how the logic they practiced in simpler environments applies to building real programs. Variables, loops, conditionals, and functions become tangible tools rather than theoretical ideas. High school students who have built a solid foundation in earlier years are ready to explore more advanced topics. Object-oriented programming, data structures, web development, app creation, and introductory computer science theory. Students at this level can build projects that are genuinely impressive. Functional websites, simple mobile applications, data analysis scripts, and interactive games. The key principle is progression. Starting early with age-appropriate tools and gradually increasing complexity produces students who develop real confidence and competence over time. Jumping straight into advanced concepts without that foundation tends to produce frustration rather than mastery. How coding connects to every school. Subject, one of the most powerful arguments for teaching coding in schools is that it does not exist in isolation. Computer science connects to and strengthens every other subject in the curriculum. Mathematics is perhaps the most obvious connection. Algebra, geometry, statistics, and logic all appear directly in programming. Writing a loop that iterates a specific number of times is applied arithmetic. Calculating the position of an object on a screen uses coordinate geometry. Sorting a list of numbers efficiently draws on mathematical reasoning. Students who learn to code often find that abstract mathematical concepts become much more concrete and meaningful when they can see them operating inside a program they have written themselves. Science benefits enormously from coding skills. Modern scientific research is deeply dependent on data analysis, simulation, and computational modeling. A student who can write a simple program to process and visualize experimental data has a skill that is genuinely useful in biology, chemistry, physics, and environmental science. As students progress, they can explore computational simulations that allow them to model physical systems, test hypotheses digitally, and visualize phenomena that are too small, too large, or too slow to observe directly in a classroom setting. Language arts and writing may seem like unlikely beneficiaries of coding education, but the connection is real. Writing clear, effective code requires the same qualities as writing clear, effective prose: precision, logical organization, attention to detail, and the ability to communicate ideas in a way that another person or system can understand. Students who learn to think carefully about the structure and clarity of their code often bring those habits of mind back to their writing. Many coding educators describe the experience of debugging a program, reading through line by line to find where the logic breaks down, as remarkably similar to the process of editing and revising a piece of writing. History and social studies intersect with computer science through the history of technology itself, through questions about how digital systems affect society, and through discussions of topics like privacy, security, algorithmic bias, and the digital divide. A student with a solid understanding of how software works is far better equipped to think critically about these issues than one who treats technology as a mysterious black box. Art and design connect to coding through digital tools for visual creation, animation, graphic design, and interactive media. Many young people who do not think of themselves as future programmers discover a deep interest in coding through creative projects, building an interactive piece of digital art, animating a short film, or designing the visual interface for an application they imagine. The intersection of technology and creativity is one of the most exciting and rapidly growing areas of the modern economy. Types of coding and computer science, software for students. The market for educational coding software has expanded dramatically over the past decade, producing a wide range of tools designed for different ages, skill levels, and learning goals. Understanding the major categories helps students and families choose the right starting point. Visual block-based programming environments are the standard entry point for younger students and absolute beginners. In these tools, code is represented as colorful, interlocking blocks that students drag and arrange to create sequences of instructions. The block format eliminates the frustration of syntax errors, a common obstacle for beginners in text-based languages, and allows students to focus entirely on learning the logic of programming. Many platforms in this category are built around game and story creation, giving students an immediate, motivating context for what they are building. Text-based beginner languages are the natural next step after block-based tools. Some programming languages have been specifically designed to be easy for new learners to read and understand, with simple, English-like syntax that reduces the cognitive load of switching from visual to written code. These languages are used in many middle and high school computer science courses and provide a genuine introduction to professional-style programming. Learning the fundamentals in a forgiving, readable language gives students a strong foundation before moving on to more complex tools. Web development tools introduce students to the languages and technologies used to build websites and web applications. Learning to create a web page, combining structure, visual style, and interactive behavior, gives students an immediate, visible result that they can share with friends and family. Web development is also one of the most practical and versatile skill sets in the technology industry, and a student who builds a strong foundation in this area has opened the door to a wide range of career opportunities. Game development software is one of the most effective ways to engage students who might not be motivated by more traditional programming exercises. Building a game requires students to think through logic, design, user experience, and problem solving all at once. Many professional game development tools offer educational versions specifically designed for students, and the experience of completing a playable game, even a simple one, provides a powerful sense of accomplishment that motivates continued learning. Data science and analysis tools are increasingly important as data becomes one of the most valuable resources in the modern economy. Software that allows students to work with real data sets, create visualizations, and draw conclusions from evidence teaches both programming skills and the kind of analytical thinking that is valued across science, business, social research, and many other fields. Even basic familiarity with data analysis concepts gives students a meaningful advantage in college and in the job market. Robotics and hardware programming platforms bridge the gap between software and the physical world. Programming a small robot or electronic device to respond to sensors, move in specific patterns, or complete simple tasks makes the abstract logic of code suddenly tangible and real. Many students who struggle to stay engaged with screen-based programming come alive when they see their code producing visible physical results. Robotics competitions at the school and regional level also provide exciting, high-stakes context for students to apply and deepen their skills. Cybersecurity education tools introduce students to the principles of protecting digital systems and information. As the world becomes more connected and more dependent on software, the ability to understand and prevent security vulnerabilities becomes more critical. Educational platforms in this category teach students to think like both defenders and attackers, understanding how systems can be compromised and how to design them to be resilient. This area is experiencing significant workforce shortages, making it one of the most promising career paths for students with an interest in technology. What students learn beyond the code itself. The benefits of studying coding and computer science extend well beyond technical skill. Research consistently shows that students who receive quality computer science education develop a range of broader competencies that improve their performance across all subjects. Problem-solving ability is perhaps the most frequently cited benefit. Programming requires students to approach problems systematically, breaking them down into components, testing solutions, identifying what works and what does not, and revising their approach based on evidence. This is not just a programming skill, it is a life skill. Students who develop strong problem-solving habits through coding tend to approach challenges in other areas with the same structured, methodical confidence. Persistence and resilience are qualities that coding naturally develops. Every programmer, at every level of experience, spends significant time debugging, finding and fixing errors in their code. A program rarely works perfectly the first time. Students who learn to code learn to treat failure not as a signal to give up, but as information that points toward the next step. This tolerance for productive struggle is one of the most valuable things a student can develop, and it is directly transferable to academic challenges in every subject. Creativity and design thinking flourish in coding environments. Despite its reputation as a purely logical discipline, programming is deeply creative. Every project requires decisions about how to structure a solution, what to prioritize, how to present information to a user, and how to balance competing goals. Students who engage seriously with coding develop an eye for design and a habit of asking not just whether something works, but whether it works well, clearly, efficiently, and elegantly. Collaboration and communication. Skills develop naturally when students work on shared coding projects. Modern software development is a team activity, and educational coding environments increasingly reflect this reality. Students learn to explain their thinking to teammates, divide complex work into components that can be developed in parallel, review each other's code constructively, and integrate their contributions into a coherent whole. These are precisely the skills that employers across every industry consistently identify as most important and most difficult to find. Attention to detail is a habit that programming rigorously enforces. A single misplaced character can cause a program to fail completely. Students who learn to code quickly develop the discipline of checking their work carefully, reading instructions precisely, and noticing small errors before they grow into larger problems. This attention to detail improves the quality of everything a student produces, in every subject. How families can support computer science. Learning at home, parents do not need to know how to code themselves to support their children's computer science education. There are several practical, meaningful ways that families can create an environment where coding skills grow naturally. The first and most important thing families can do is express genuine interest in what their student is learning and building, asking to see a project, sitting alongside a child while they work on a coding challenge, and celebrating completed work, even something as simple as a small game or a web page, communicates that this learning matters. Students whose parents show interest in their work are consistently more motivated and more persistent. Providing access to appropriate tools is also important. Many educational coding platforms are entirely free, and the devices most students already have at home are more than adequate for beginning to learn. Families should check what their school already provides through educational licensing and supplement from there based on the student's interests and goals. Setting aside regular dedicated time for coding practice produces better results than occasional long sessions. Like learning a musical instrument or a foreign language, coding skill grows most reliably through consistent repeated practice. Even 20 to 30 minutes several times a week adds up quickly over a school year. Connecting coding to things the student already loves can dramatically increase engagement and motivation. A student who is passionate about music might be excited to explore how software is used to produce, mix, and distribute audio. A student who loves sports might be interested in how data analysis is used in professional athletics. A student who enjoys drawing or graphic design might be drawn to digital art tools and animation software. The entry point matters far less than the engagement it creates. Families can also look for community programs, after-school clubs, summer camps, and online learning communities that extend computer science education beyond the classroom. Many of these programs are free or low cost, and they provide students with peer communities of fellow learners, which is enormously valuable for sustaining motivation over the long term. The career landscape for students who study computer science, one of the most compelling reasons to invest in computer science education is the extraordinary range of career opportunities it opens. Technology skills are now relevant in virtually every industry, not just in companies that build software. Healthcare organizations need professionals who can manage and analyze patient data, build electronic health systems, and develop medical devices. Financial institutions need people who can build secure transaction systems, analyze market data, and detect fraud algorithmically. Manufacturing companies need engineers who can program automated systems, analyze production data, and design efficient supply chains. Media and entertainment companies need professionals who can build streaming platforms, develop interactive experiences, and manage enormous volumes of digital content. Even fields like agriculture, architecture, education, law, and social work are increasingly relying on software tools, and the professionals who understand those tools at a deeper level than just a surface user are consistently more effective and more valuable. The economic data on this point is clear and consistent. Careers that require computational skills tend to offer higher starting salaries, stronger job security, faster advancement, and more flexibility in terms of where and how work is performed. For students from lower income backgrounds in particular, computer science education has proven to be one of the most reliable pathways to economic mobility. But the value of computer science education is not only economic. Students who understand how technology works are better positioned The future of educational technology. Introduction. Standing at the threshold of a new era. Education has always evolved. The invention of the printing press democratized access to books. The establishment of public school systems made education available to children who had previously been excluded from formal learning. The development of universities created spaces where knowledge could be pursued, tested, and expanded at the highest levels. Each of these transformations took generations to fully unfold, and each one changed not just how education was delivered, but what education was understood to be. We are living through another transformation of that magnitude right now. The technologies emerging in the early decades of the 21st century are not simply making existing educational practices faster or more convenient. They are fundamentally changing what is possible in a learning environment, who can learn, what they can learn, how they can learn it, and how quickly they can progress from beginner to mastery. The pace of this transformation is faster than anything previous generations experienced. A teacher who began their career 20 years ago and a teacher beginning their career today are operating in recognizably different professional environments. The tools, the expectations, the possibilities, and the challenges have all shifted dramatically. And the technologies that will define education 20 years from now are already being developed and tested in classrooms, research labs, and technology companies around the world. Understanding where educational technology is heading is not just relevant for educators and school administrators. It matters for every parent who wants to prepare their children for the world they will actually inhabit, for every student making decisions about what to study and how to invest their time, and for every citizen who has a stake in whether the education system produces informed, capable, adaptable human beings. This is an exploration of that future, what the technologies are, how they will change learning, what the opportunities are, and what the risks and challenges must be honestly confronted along the way. Artificial intelligence and personalized learning. Of all the technologies reshaping education, artificial intelligence is the most transformative and the most far-reaching in its implications. To understand why, it helps to start with one of the oldest and most persistent problems in education, the tension between standardization and personalization. For most of the history of formal schooling, education has been delivered to groups. One teacher stands before 30 students and presents the same material at the same pace, in the same format, on the same schedule. This approach is efficient in a logistical sense. It allows one trained professional to serve many students simultaneously, but it is profoundly inefficient in a learning sense because every one of those 30 students is different. They have different prior knowledge, different strengths and gaps, different learning styles, different speeds of processing new information, and different motivations. The result is an unavoidable compromise. The pace of instruction is set somewhere in the middle, too fast for students who are struggling, too slow for students who are ready to move ahead. The format of instruction suits some students well and others poorly. The examples and contexts used to illustrate concepts resonate deeply with some students and barely register for others. Every teacher knows this is happening, and every skilled teacher works hard to address it, differentiating instruction, providing extra support here and extension opportunities there. But there are limits to what any individual human instructor can do for 30 different learners simultaneously. Artificial intelligence changes this equation fundamentally. An AI-powered learning system can monitor every interaction a student has with the material in real time. It can detect, with considerable precision, exactly where a student's understanding is solid and where it is fragile. It can adjust the difficulty, format, pacing, and sequence of what it presents based on that understanding, not at the end of a unit when a test reveals gaps, but moment by moment as learning is happening. It can offer a different explanation when the first one does not land, a different example when the standard one is not connecting, a different type of problem when the student has demonstrated mastery and is ready to be challenged further. This is not science fiction. Adaptive learning systems operating on these principles already exist and are being used in schools around the world. The current generation of these tools is impressive. The next generation, built on more powerful AI architectures and trained on vastly larger data sets of student learning behavior, will be significantly more capable. The implications extend beyond individual students. AI systems that aggregate learning data across many students can identify patterns that would be invisible to any individual teacher. Noticing, for instance, that a particular explanation of a mathematical concept consistently produces misconceptions, or that a specific sequence of topics leads to better long-term retention than the sequence traditionally used in textbooks. These insights can improve not just individual learning experiences, but the design of curricula and instructional materials at scale. There are legitimate questions and concerns about AI in education that must be addressed seriously. Data privacy is paramount. The learning data generated by students is sensitive, and the systems that collect and analyze it must be designed and governed with the highest standards of protection. The risk of algorithmic bias must be actively monitored and corrected. If an AI system is trained on data that reflects historical inequities in education, it may perpetuate or even amplify those inequities rather than reducing them. And the relationship between human teachers and AI tools must be designed thoughtfully, ensuring that technology supports and enhances the work of educators rather than displacing the irreplaceable human elements of teaching. None of these concerns is a reason to avoid AI in education. They are reasons to approach it with intelligence, care, and a clear commitment to the values that should guide all educational technology: equity, effectiveness, and the dignity and development of every student. Virtual and augmented reality in the classroom. There is a category of educational content that has always been genuinely difficult to teach well. History comes to life in museums and historical sites, but most students will never visit the places where the events they are studying actually occurred. Biology is most vividly understood by examining living organisms, but dissections are limited, and many of the most interesting biological phenomena happen at scales or speeds that are invisible to the naked eye. Physics concepts like orbital mechanics, wave behavior, and quantum phenomena involve systems that are too large, too small, or too abstract to observe directly. Architecture and engineering require spatial reasoning skills that are hard to develop from two-dimensional diagrams. Virtual and augmented reality technologies offer a direct response to these challenges. A student wearing a virtual reality headset can stand in ancient Rome as it appeared at the height of the empire, walk through a rendered model of the human heart, and observe its chambers and valves in operation, or experience the scale of the solar system in a way that no diagram or video can convey. An augmented reality application can overlay a three-dimensional model of a molecule onto the student's physical desk, allowing them to rotate it, zoom in on specific bonds, and explore its structure from every angle. The educational value of these experiences is not merely motivational, though motivation matters enormously. Research on learning consistently demonstrates that people understand and retain information better when they experience it in multiple modalities, not just reading about something or hearing it described, but seeing it, interacting with it, and experiencing it in a context that feels real and meaningful. Virtual and augmented reality expand the range of experiences that are possible within a classroom to an extraordinary degree. The technology is still maturing. Current virtual reality hardware is expensive, physically cumbersome, and not yet comfortable for extended use, particularly by younger children. The content libraries available for educational virtual reality, while growing, are still limited compared to what will be possible as more developers invest in creating high-quality experiences. Augmented reality is more accessible. It can run on smartphones and tablets that many students already have, but the experiences currently available are still relatively simple compared to what the technology will eventually deliver. Over the next decade, both of these trajectories will change significantly. Hardware costs will fall, devices will become smaller, lighter, and more comfortable. Content libraries will expand, and the integration of artificial intelligence with virtual and augmented reality will enable experiences that respond dynamically to what individual students do within them, creating truly interactive, adaptive, immersive learning environments. Consider what this will mean in practice. A history student will not just observe a rendered version of a historical environment, but will be able to interact with it, making decisions, experiencing consequences, and developing a genuinely embodied understanding of the constraints and choices that real historical actors faced. A medical student will be able to practice surgical procedures in a simulated environment that provides realistic feedback, builds genuine muscle memory, and allows for mistakes that would be catastrophic in a real operating room. An engineering student will be able to test the structural integrity of a bridge design by applying simulated loads and observing how the structure responds, learning through direct experience rather than abstract calculation. These are not distant possibilities. They are developments that are underway right now, and the students who begin school in the next 5 to 10 years will encounter versions of these experiences as a normal part of their education. The evolution of the classroom and the role of the teacher. As technology takes on more of the tasks that have traditionally been performed by teachers, delivering content, assessing understanding, providing feedback, adapting instruction to individual needs, a fundamental question arises. What is the role of the human teacher in this new landscape? The answer, examined honestly, is that the role of the teacher becomes more important, not less, but it changes significantly in character. The aspects of teaching that can be automated are, by and large, the aspects that are least uniquely human. Delivering a lecture on the causes of the First World War can be done by a well-designed video. Administering a quiz on vocabulary words and scoring the results can be done by software. Identifying which students are struggling with quadratic equations and providing targeted practice problems can be done by an adaptive learning system. What cannot be automated is the human relationship at the heart of great teaching. The teacher who notices that a student who was previously engaged has become withdrawn and takes the time to find out why. The teacher who recognizes genuine intellectual potential in a student who has been written off by others and nurtures it with patience and high expectations. The teacher who models intellectual curiosity, ethical seriousness, and love of learning in ways that students absorb not from a lesson plan but from sustained proximity to an admirable adult. The teacher who facilitates a classroom discussion in which students with genuinely different perspectives have to grapple seriously with each other's ideas and emerge with more nuanced understanding than any of them brought in. These are the things that matter most about teaching, and they are precisely the things that technology cannot replicate. As AI and other tools take on more of the routine cognitive labor of instruction, teachers will have more time and energy for these deeply human dimensions of their work. The teacher of the future is less a deliverer of content and more a designer of learning experiences, a coach of intellectual development, a mentor of personal growth, and a curator of the human connections that make learning meaningful. This shift will require significant changes in how teachers are trained, how they're evaluated, and how schools are organized. Teacher education programs will need to prepare educators to work effectively alongside technology, understanding what AI tools can and cannot do, designing learning environments that integrate digital and human elements thoughtfully, and developing the skills of facilitation, coaching, and mentorship that will define excellent teaching in the decades ahead. Schools themselves will change in their physical design and organizational structure. If students can access high-quality content instruction at any time through digital platforms, the physical classroom becomes less a place for content delivery and more a place for collaborative work, discussion, hands-on projects, and the kinds of interactions that require human presence. Many schools are already experimenting with this model, and the results consistently show that students are more engaged, more motivated, and more capable of applying what they have learned when the classroom is organized around active participation rather than passive reception. Global connectivity and learning without borders. One of the most profound implications of educational technology is geographical. For most of human history, the quality of education a child received was determined almost entirely by where they happened to be born. A child born in a wealthy city with excellent schools had access to opportunities that were simply unavailable to a child born in a rural community, a developing country, or a region affected by conflict or poverty. This geographic lottery of educational opportunity has been one of the most persistent and consequential sources of inequality in human society. Technology is not going to eliminate this inequality overnight, and it would be naive to suggest otherwise. Access to devices, reliable internet connections, and electricity remains unequal across the world, and closing these gaps requires sustained investment and policy commitment. But the direction of travel is clear, and the progress being made is real. The fundamental economics of educational content have changed. A high-quality course, lecture series, or educational program that once required physical attendance at a specific institution can now be delivered to anyone in the world with an internet connection. A student in a small town with no access to advanced courses can study subjects that were previously available only to students at well-resourced schools in major cities. A student in a developing country can access educational content created by the world's leading experts and institutions in their own language, at their own pace, for free or at very low cost. Language barriers, which have historically limited the geographic reach of educational resources, are falling rapidly. Machine translation technology has improved to the point where high-quality educational content created in one language can be automatically translated into many others with reasonable accuracy. As these tools continue to improve, the vision of a global library of educational resources, accessible to every learner, regardless of their native language, comes steadily closer to reality. Global connectivity also creates new possibilities for collaboration between students across different countries and cultures. A history project that involves students from 3 different countries examining the same historical event from their respective national perspectives produces a richer, more nuanced understanding than any single nation approach could achieve. A science project that collects data from student researchers in multiple locations creates data sets of a scope and diversity that no single classroom could generate. These kinds of globally collaborative learning experiences are already happening, and they will become more common and more sophisticated as the tools that support them improve. For educators, global connectivity means access to a worldwide community of professional practice. A teacher in a rural school who might previously have had limited contact with colleagues outside their immediate district can now participate in professional learning communities with educators from around the world, sharing approaches, discussing challenges, and learning from the full diversity of global educational practice. This democratization of professional development has the potential to raise the quality of teaching everywhere, not just in well-resourced institutions, and data, assessment, and the end of the annual exam. The way student learning is assessed is one of the aspects of education most urgently in need of transformation, and technology is providing the tools to make that transformation possible. Traditional assessment, the end-of-unit test, the midterm exam, the annual standardized assessment, has several well-documented limitations. It provides a snapshot of what a student could demonstrate on a single day under particular conditions, which may or may not accurately reflect their actual understanding. It measures a narrow range of skills and knowledge, systematically undervaluing capabilities like creativity, collaboration, problem-solving, and communication that are deeply important but difficult to assess through multiple-choice questions. It produces results too slowly to be useful for instructional decision-making. By the time a teacher receives information about how their class performed on an assessment, the class has moved on to new material, and it creates significant anxiety for many students, particularly
Today, we are talking about school and family collaboration and why it is important for student success. Strong communication between parents, teachers, and schools creates a positive learning environment for children. When families and schools work together, students often feel more supported, motivated, and confident in their education. One important tip for successful collaboration is regular communication. Parents should stay in contact with teachers through emails, meetings, school apps, or phone calls. Teachers can also provide updates about student progress, homework, attendance, and classroom activities. Clear communication helps avoid misunderstandings and builds trust between families and schools. Another helpful strategy is creating a positive home learning environment. Families can encourage children to complete homework on time, read books regularly, and maintain good study habits. Even small daily conversations about school activities can improve student confidence and academic performance. Schools should also encourage parents to participate in school events. Activities such as parent meeting, sports events, cultural programs, and educational workshops help families feel connected to the school community. When parents are involved, students often become more engaged in learning. Respect and understanding are also very important. Every family has different backgrounds, schedules, and challenges. Schools should create welcoming environments where all parents feel respected and valued. Families should also support teachers and understand the efforts they make to help students succeed. Technology can improve school-family collaboration as well. Educational platforms, online learning systems, and messaging applications make communication faster and easier. Parents can quickly check announcements, assignments, and school updates from their phones or computers. Setting shared goals is another useful tip. Parents and teachers can work together to support academic improvement, better attendance, positive behavior, and emotional well-being. When adults cooperate and focus on the same goals, children receive stronger support. Encouraging student responsibility is equally important. Families and schools should teach children how to manage time, complete tasks independently, and communicate respectfully. These skills prepare students for future education and career success. Mental health and emotional support should also be part of collaboration. Schools and families can help students manage stress, build confidence, and develop healthy social relationships. Open conversations about emotions and well-being create a safer environment for children. Community partnerships can strengthen education too. Schools may collaborate with libraries, sports organizations, local businesses, and educational programs to provide additional opportunities for students. These partnerships can improve learning experiences and support personal development. In conclusion, school-family collaboration plays a major role in student achievement and personal growth. Through communication, respect, participation, and shared goals, families and schools can create strong support systems for children. Positive collaboration helps students develop confidence, responsibility, and motivation for lifelong learning. Today, categories of educational software and how these digital tools are transforming modern learning. Educational technology has become an important part of schools, universities, workplaces, and home learning environments around the world. Software applications help students improve knowledge, teachers organize lessons, and institutions manage education more effectively. The 6 categories we will discuss today are learning management systems, productivity software, research software, math and science software, language learning software, and organization software. Each category serves a different purpose, but together they create a complete digital learning ecosystem that supports education for students of all ages. Let us begin with the first category, learning management systems, often called LMS platforms. A learning management system is software designed to manage, deliver, and track educational courses or training programs. Schools, universities, and companies use LMS platforms to organize online learning. These systems allow teachers to upload lessons, assignments, quizzes, and videos, while students can access materials, submit homework, and communicate with instructors. Popular LMS platforms include Moodle, Google Classroom, Canvas, Blackboard, and Schoology. These systems became especially important during the growth of remote and online education. Students can learn from home while teachers monitor attendance, participation, and academic progress digitally. One major advantage of LMS platforms is accessibility. Students can study at their own pace and access learning materials anytime using computers, tablets, or smartphones. Teachers can also save time by automating grading and organizing coursework efficiently. Another important feature is communication. Discussion boards, announcements, messaging systems, and virtual classrooms help students and teachers stay connected. Many LMS platforms also include analytics tools that help educators identify students who may need additional support. However, there are challenges as well. Some students may struggle with internet access or lack technical skills. Teachers also require training to use LMS platforms effectively. Despite these challenges, LMS software continues to play a major role in modern education and digital learning. Now let us move to the second category, productivity software. Productivity software helps students and educators create, edit, and manage educational work more efficiently. This category includes word processors, spreadsheets, presentation tools, note-taking applications, and collaborative platforms. Examples include Microsoft Word, Excel, PowerPoint, Google Docs, Google Sheets, Google Slides, Notion, and OneNote. These tools support everyday academic tasks, such as writing essays, preparing presentations, analyzing data, and organizing projects. Word processing software allows students to create professional documents with formatting, spelling correction, and editing tools. Teachers often use these applications to prepare lesson plans, exams, and reports. Spreadsheet software is useful for mathematics, statistics, finance, and scientific analysis. Students can organize data, create charts, and perform calculations using formulas. This develops problem-solving and analytical skills. Presentation software helps students communicate ideas visually through slideshows, graphics, animations, and videos. Presentation skills are important in both academic and professional environments. Collaborative productivity tools have become increasingly popular. Students can work on group assignments together in real time, even when they are in different locations. This encourages teamwork, communication, and digital collaboration skills. Productivity software improves efficiency and creativity, but it also requires responsible use. Students must learn time management and avoid distractions while using digital devices. The third category is research software. Research software helps students and educators find, analyze, organize, and reference information. In today's digital world, research skills are essential because information is available everywhere online. Educational software makes research faster, more accurate, and more organized. Examples of research tools include Google Scholar, JSTOR, Zotero, Mendeley, EndNote, online libraries, educational databases, and encyclopedia platforms. Search engines and academic databases allow students to access scientific articles, books, journals, and educational publications. This supports deeper understanding and evidence-based learning. Citation management software helps researchers organize references and automatically generate citations in different academic formats, such as APA, MLA, or Chicago style. This saves time and reduces mistakes in academic writing. Research software also encourages critical thinking. Students learn how to evaluate reliable sources, compare information, and avoid misinformation. Digital literacy is an important skill in modern education because not all online information is trustworthy. Another important aspect is accessibility to global knowledge. Students can access educational materials from universities, research institutions, and experts around the world. This expands learning opportunities beyond traditional classrooms. However, research software also presents challenges. Students may face information overload due to the large amount of online content available. Educators must teach students how to identify credible sources and use information ethically. The fourth category is math and science software. Math and science software supports learning in subjects as mathematics, physics, chemistry, biology, engineering, and computer science. These tools help students visualize concepts, solve problems, perform experiments, and improve technical skills. Examples include GeoGebra, MATLAB, Wolfram Alpha, Desmos, PhET simulations, Scratch, coding platforms, and virtual science laboratories. One major advantage of math and science software is visualization. Complex equations, graphs, and scientific processes become easier to understand through interactive models and simulations. For example, graphing software allows students to explore algebraic equations visually. Science simulation software enables students to conduct experiments safely in virtual environments without expensive laboratory equipment. Coding and programming platforms also belong to this category. Learning programming helps students develop logical thinking, creativity, and computational problem-solving skills. Many schools now teach coding as part of modern education. Virtual labs became especially valuable during remote learning periods. Students could continue science experiments online even when physical classrooms were unavailable. Math and science software also supports personalized learning. Students can practice at their own pace and receive immediate feedback on exercises and quizzes. Challenges include software complexity and technical requirements. Some advanced scientific tools require powerful computers and training. Nevertheless, these applications significantly improve STEM education and prepare students for future careers in science and technology. Now let us discuss the fifth category, language learning software. Language software helps students improve speaking, listening, reading, writing, vocabulary, and pronunciation skills in different languages. Global communication and international opportunities have increased the importance of language education. Examples include Duolingo, Babbel, Rosetta Stone, Grammarly, language dictionaries, pronunciation tools, and translation applications. Language learning software often uses interactive exercises, quizzes, games, and audio recordings to make learning engaging and enjoyable. Many applications adapt lessons based on the learner's progress and skill level. Speech recognition technology helps learners practice pronunciation and receive feedback instantly. This improves confidence and communication abilities. Writing tools such as grammar checkers support students in improving grammar, spelling, punctuation, and sentence structure. These tools are useful for academic writing and professional communication. Another advantage is flexibility. Students can practice languages anytime and anywhere using mobile devices. Short daily lessons help learners maintain consistent progress. Language software also exposes students to different cultures, accents, and communication styles. This supports global understanding and intercultural communication skills. However, software cannot completely replace human interaction. Real conversations with teachers and native speakers remain important for fluency and social communication development. The sixth and final category is organization software. Organization software helps students and educators manage schedules, assignments, notes, deadlines, and educational responsibilities. Effective organization improves productivity, reduces stress, and supports academic success. Examples include Google Calendar, Trello, Todoist, Evernote, Microsoft Outlook, Notion, and digital planners. Students often manage multiple subjects, projects, exams, and extracurricular activities. Organization software helps them plan tasks and prioritize responsibilities efficiently. Digital calendars provide reminders for deadlines, classes, meetings, and exams. Task management applications allow users to create checklists and track progress on assignments. Teachers also benefit from organization tools. They can schedule lessons, monitor grading timelines, coordinate meetings, and manage classroom activities more effectively. Cloud-based organization software allows users to synchronize information across multiple devices. Students can access schedules and notes from phones, tablets, or computers anytime. Good organizational skills are valuable beyond education. Time management and planning abilities are important in workplaces and personal life as well. Despite these benefits, students must avoid becoming overly dependent on technology. Strong personal discipline and responsibility remain essential for effective learning and organization. Now that we have explored the 6 categories, let us discuss how these educational technologies work together in modern learning environments. In many schools and universities, multiple software categories are integrated into one digital system. For example, a student may use an LMS platform to access assignments, productivity software to complete projects, research tools to gather information, math software to solve equations, language applications to improve writing, and organization software to manage deadlines. This integration creates a flexible and connected learning experience. Technology supports communication, collaboration, creativity, and independent learning. Educational software also supports inclusive education. Students with disabilities may use assistive technologies such as text-to-speech software, screen readers, subtitles, and adaptive learning systems. These tools help create equal learning opportunities for diverse learners. Artificial intelligence is also becoming more common in educational software. AI systems can personalize lessons, recommend exercises, provide instant feedback, and analyze student performance. Adaptive learning platforms adjust content based on individual progress and learning speed. Virtual reality and augmented reality are additional innovations. Students can explore historical sites, scientific environments, and interactive simulations through immersive educational experiences. Cybersecurity and digital safety are important topics as well. Schools and students must protect personal data, maintain secure passwords, and use educational platforms responsibly. Teachers continue to play a central role despite technological advancements. Software is a tool that supports education, but human guidance, mentorship, and emotional support remain essential for student development. Parents also contribute to successful educational technology use. Families can encourage balanced screen time, monitor online activities, and support healthy study habits at home. The future of educational software will likely include more personalized learning, global collaboration, AI assistance, and mobile accessibility. Technology will continue evolving as education adapts to changing social and professional needs. In conclusion, the 6 categories of educational software each play a valuable role in modern learning. Learning management systems organize education digitally. Productivity software improves efficiency and collaboration. Research software supports information gathering and academic analysis. Math and science software enhances technical understanding through visualization and simulations. Language learning software improves communication skills. Organization software helps students manage time and responsibilities effectively. Together, these technologies create dynamic learning environments that support students, teachers, and educational institutions around the world. Educational software encourages creativity, flexibility, communication, and lifelong learning. As technology continues developing, digital education tools will remain an important part of the future of learning and global knowledge sharing.